Well, hey guys, sorry I'm not there today. I am at home taking care of the girls. Lexi got a positive test for influenza type A, so she's got the flu. So I'm trying really hard not to get sick. So there's a decent chance I will not see you tomorrow either, but oh well. Let's get right into this stuff. So we've already talked a lot about scatter plots and line of best fit. Not a lot, but some. I do want to talk about this new idea up here of correlation coefficient, and that just has to do with how closely the data can be modeled by a line. So let's just get right into some examples here. So if you had a scatter plot and there was a strong positive correlation, so if we were in this block right here, what would that look like? So go ahead and draw this. So we're going to draw a scatter plot here. So we're going to do like an XY axis. And I want you to imagine if we had a bunch of points on here and we were going to draw a line to fit the data. Basically, what a strong correlation means is that when you draw the line, it's going to fit the dots really closely. Like it will almost go through just about every dot. Okay, so imagine if we had a bunch of dots here that were plotted, and I'm not going to say what the axes are here, but imagine we just had a ton of dots here that were plotted. See how we can almost perfectly fit a line on this data if we draw this line right here? That line of best fit, it almost goes through like every point. It's really close. So that's a strong positive correlation. Why is it called? So it's strong because the line is close to the dots. It's positive because as the X value increases, or as the input increases, the output also increases. So we say that there's a positive relationship there. In other words, as one value goes up, the other value goes up. Let's actually do a strong negative correlation. So what we're going to do is we're going to draw a similar thing here. So we'll draw the XY axis. A strong negative correlation is the same idea. The line will be close, but instead of as one variable goes up, the other goes up, this one will be as one variable goes up, the other one goes down. So that's what a negative correlation is. You don't need to draw a ton of dots here. But basically what's happening here is as the X goes up, the Y values go down. And so that's what it means to be a negative correlation. Really important note here. The strength of the correlation doesn't have anything to do with how steep your line is, okay? You could have a line that's this steep that has a really weak correlation, okay? And we'll actually show you a couple examples of that here, okay? So, all right. So that's strong correlation with positive and negative. Let's say we had a moderate correlation, but it was positive. So I want to fill out this box right here. So a moderate positive correlation. Let's go ahead and draw that. So we got our XY axis. So we're still going to have a positive correlation, but it's not going to be as strong. We're not going to be able to predict the output quite as closely as we would be able to with a strong correlation. So what would this look like? This would look probably something like this. So we've still got a positive correlation here, but these dots are kind of more spread out. We can still somewhat comfortably fit a line to it, but the dots are a little more spread out. Okay, so that's a moderate positive correlation. Let's do a moderate negative correlation. It's going to be the same idea, except instead of going up, we're going to go down as we go from left to right. So a moderate negative correlation is going to be, we can still kind of predict with a line here, like we're going down, but it's not quite as strong. So that's a moderate negative correlation. That actually might be a little more toward the weak end of correlation, but whatever. You get the point. How about weak correlation? So weak correlation is going to be if we draw our XY axis here. A weak positive correlation is going to be a positive correlation, but not very strong. This line is barely going to be able to kind of predict. So like we got dots all over the place here. And the general idea is, look, as you tend to go right, you go up, but like it's not very strong, right? So like this dot here and then this dot here, if you go right, you actually go down a little bit if you just look at those two dots. But as a general rule, we're kind of trending up as we go from left to right, right? So as x gets bigger, the y values kind of tend to get bigger. So that's a weak positive correlation. You can probably figure out what a weak negative correlation would be then, right? So it's going to be the same idea, except we're going to kind of trend down a little bit. So basically these dots over time will generally tend to kind of trend down. But it's hard to make any super accurate predictions because a lot of these dots are not really close to the line. Okay? And that brings us to this idea of correlation coefficient. So the correlation coefficient is just a number that you're going to get that tells you how, it's a measure of how closely that line actually fits to those data points, okay? So stronger correlations tend to be closer to 1 and -1, okay? So imagine, and we'll get back to, I promise we'll do these graphs over here in a sec, but I want to talk about the correlation coefficient. Imagine a number line here. Oops, why am I drawing green all over the place? Imagine a number line here, and on the ends you've got -1 over here, and then you've got +1 right here. In the middle you've got 0. Okay, and so what happens here is you've got, on the positive side, if you go between 0 and 1, this is going to be a weak positive correlation in this zone right here. So if you happen to fall between 0 to, like 0.2 or 0.3, that's generally considered kind of a weak positive correlation. Okay, so if you get a correlation coefficient of like, let's say 0.10, that's a pretty weak positive correlation. Most people wouldn't even, if you were looking at a statistical study, most people, if you said, oh yeah, the correlation coefficient was 0.10, they would say, we don't really think that there's really much of any correlation there. Okay, so, and then you get into this zone right here, and this is kind of a moderate positive correlation. So there's no like set rule on this, but like generally if you're between like 0.3 and like 0.6 roughly, we kind of say, all right, so that's a pretty decent correlation there. There does seem to appear to be some relationship between the input and the output, and you can kind of predict the output based off of the input. And then once you fall over in this range, we consider this like a strong positive correlation. So there's no hard and fast number here that you're looking for, but like generally kind of 0.6 or 0.7 and above, we're pretty excited in statistics when we see a number like that, because that means that we've got a very strong relationship and you can predict the output with pretty decent accuracy based off of the input. And that's what we want in statistics, is when we measure things, we want to be able to find the relationship and use an equation to model it and then make predictions about it. Okay, so let's go on the other side then. If you go over on the but on the negative numbers, it's the exact same thing, just the other way around. So you're looking at like from here to here is going to be a weak correlation because you're close to 0, but it's going to be a weak negative correlation, which means as one value goes up, the other value tends to go down. And then from here to here is where we call this a moderate negative correlation. Right? So there does appear to be a correlation that's decent, but it's a little tricky to predict what the output will be given the input. But you can still make a little bit of a prediction. And then this we would consider the strong negative correlation, right? So we have figured out there's definitely a correlation. It's definitely negative. As one value goes up, as the input value goes up, the output value goes down, and we can predict it pretty accurately. Okay, so that's how the correlation coefficient works. Okay, so let's actually come up here and look at these and give what might be a reasonable correlation coefficient here on these. So if you were looking at these scenarios, I would say a reasonable correlation coefficient here would be R is, I'm not going to put actually equal to, I'm going to put like a squiggly equal to sign. We're going to say the correlation coefficient here is probably about 0.90 or 0.95, right? So it's pretty close to 1. Okay, and it's positive because it's a positive correlation. It's going up from left to right. How about this one right here? What would a good guess for a correlation coefficient be here? So I would say this one's probably about a negative 0.95. Okay, it's the same number. It's just negative because it's a negative correlation. Again, it has nothing to do with the slope here. It just has everything to do with how closely that line actually hits those data points. Okay. Moderate correlation, I'm just throwing out a guess here. You can mathematically determine these things. This is probably about like 0.6 or something like that. Okay, so that's probably about 0.6. This one will say the same thing. It's probably about 0.6, but it's negative because it's a negative correlation. And then on these, we'll probably say the correlation coefficient is roughly, I don't know, like 0.20. So it's hardly giving us any predictive power as far as guessing what the output will be given the input. Okay, so that's how correlation coefficient works. It's always going to be between -1 and +1. Okay, the closer you get to the edges here, like -1 and +1, the stronger your correlation is. The closer you get to 0, the weaker your correlation is. All right, no correlation examples. So we have some examples where there's just like no discernible correlation, right? And so those examples would be like if you had dots just all over the place, like, and there's no way to determine like, oh yeah, it definitely looks like it's going up or down, right? Like this is just all over the place. There's no way to determine a relationship between the input and output. There are a couple other examples. I don't know if there are a ton of examples like this in the real world, but like mathematically we should talk about them. If you have something like this that's just like straight up and down, there's no correlation there, okay? Like just because you have an output doesn't mean you can predict the input. And because the input is always the same, right? Like whatever, I don't know, whatever this number is, 7, the input is always like about 7. And then the other example is just the flip side of this, just like a totally flat curve. Like there's no correlation here between the input and the output. Like it's just a flat line here at this, at whatever this output is. So you're not able to predict the output based off of the input on this. So yeah, like the output here would always be whatever that number is right there. So maybe, I don't know, I guess you can predict it, but it has nothing to do with the input, right? And that's what's important about the study of this subject. Okay, so that's that. And then what I want to do is look at some examples of like scatter plots and line of best fit and correlation coefficient. And we have kind of covered this stuff already a little bit, so I'll try to go through this relatively quickly. They want us to plot the data pairs on the coordinate plane below and then answer the questions. So I'm just going to do 1, 100. So 1, 100 is right there. 2, 70. Let's go ahead and drop that dot there. 3, 80. Next one is 3, 85. Okay, so I guess we have multiple outputs for 3. 3, 75. 4, 65. 5, 90. 5, 60. That's a big difference. 6, 40. 7, 45. 7 with 55. 8 with 20. I actually can't even get to 20. Where would 20 would be like down here if we graphed it. So I'll just put a point there just to be funny. And then 940. So 940 is about right there. Okay, so that's number 1. So make a scatter plot. We're done with that. Number 2, decide whether the data can be modeled by a line. Does the data have positive or negative correlation? I would say, yeah, we could probably fit a line to this. It's not like super accurate, but we could probably do about that. Like, that's probably a pretty decent line there. So I would say, yeah, we could probably do that. That's definitely a negative correlation, right? So as the x values go up, the y values go down. Okay, so number 3 says draw a line that fits the data closely. And a nice tip on this is there should be approximately as many data points above the line as are below it. Okay, all right, number 4, write an equation using 2 points on the line. So I'm just going to grab some points on the line, and if possible, I always love to grab the y-intercept, which it looks like is about 105. And then I'll just try to grab a point that's relatively close to like an actual nice corner point. Like this is real nice right here. See how this goes like right through that corner there? So that's it. I don't like decimals. See how it's at like 2.5, comma 80. Let's actually go back here. Let's do 2, comma 85. That'll just make our math a little easier. I try to avoid fractions if at all possible. Okay, write an equation using 2 points on the line. So the points don't have to be actual data pairs, but they must lie on the line of best fit, right? So notice how these blue points aren't actually from the data set here. Like I just kind of manufactured them based off of the line. That's okay, as long as they're on the line. So what we've got here is we've got a y-intercept of, let's just say 105. So the y-intercept is 105. So I'm going to say y is equal to something plus 105. Because that's the y-intercept. And I'm thinking y equals mx plus b here, right? So mx plus b, where b is the y-intercept, and then m is the slope. So the y-intercept's 105. What is the slope on this line? So that's just a measure of how much we're going down and how much we're going over, right? So we've got to get from this blue point to this blue point. To me, it looks like we're going from 105 to 85, so it looks like we're going down 20. So the slope in this case is going to be down 20 and then over. Let's be careful here. We're going over 1, 2, 3, 4 boxes, but are we actually going over 4? No, to get from here to here is a difference of, if you look, it's a difference between 0 and 2. So it looks to me like we're going over 2. So what is the slope actually? If you have negative 20 over 2, that's actually negative 10. So the slope here is negative 10x plus 105. Okay. Number 5, is there a correlation? What do you think the correlation coefficient would be? So yes, I would say yes, there is a, I would say probably a moderate negative correlation. Moderate negative correlation. And as far as the correlation coefficient, if I had to guess on this, I don't know. I'd probably say about, it's got to be negative, so let's say negative 0.50. Might be a little weaker than that. It's kind of hard to eyeball this unless you've done it by hand and you actually know the mathematics behind it. But, you know, could the line be fitting the dots closer? Absolutely. Could the line be not fitting them closer? Sure, yeah. These dots could be even more spread out, but they're sort of congregating around the line here. So negative 0.50 is probably a good guess on that. Okay, so if you guys really feel like you understand what you're doing right now, you're going to have to ask yourself an honest question. Do I actually understand what's happening right here, and can I go on? I want to say, if you feel like you really know what you're doing, I just want you to feel the freedom to go ahead and actually work on the homework assignment on those 2 pages there, okay? So the front and back. But if you feel like you need a little more help, definitely keep watching, okay? So example 2 gave us a table, and it gives us the ages and heights of 10 pine trees. And it actually looks like 9 pine trees, but whatever. All right, so we're going to go ahead and graph this, and then we're going to give the equation for the line of best fit. We'll describe the correlation. We'll give a rough estimate for the correlation coefficient, and then they want us to make a prediction about if it was 50 years old, how tall it would be. So let's go ahead and graph this. This one's a little tricky because they didn't give you the axes. They didn't give you the scale on this, so you're going to have to decide this on your own. And you're going to have to figure out what you want the independent variable to be and what you want the dependent variable to be. So I'm assuming what they would like us to do is to predict the height as a function of the age. So in other words, the age will be down here on the independent axis, and the height will be dependent based off of the age. And with trees, there's definitely a positive correlation, right? The older the tree is, the taller it is. So, all right, we've got to be able to cover on the height. We got to get from, basically, I'm going to say down to 0, right? This is at 2 here, but we should probably start at 0. And we've got to get up to 35 for the height. So how many boxes do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have 16 boxes. We got to cover 35 years. Gosh. Maybe the easiest thing to do here is to just go by 5s. I mean, look, we could go by like 3s, but I don't like going by 3s. That's weird. You can do it if you want, but I'm going to go by 5s. So on the x-axis, I'm going to go... Every box is going to be 5 years. So 5, 10, 15, 20, 25, 30, 35, 40, and then it only goes up to 35 here. So I'm not going to bother going much further. Please make sure to label your axes too. So this is going to be in years. So maybe what we'll do is we'll say age, and then typically a lot of times what we'll do is we'll say what we're measuring, and then we'll put the unit right here. Okay, next thing we need is the height, and that's going to be in feet. So what we're going to do is we're going to come over here and we're going to say height of the tree, and we're going to measure that in feet. And let's figure out how we want to scale this. So we've got to be able to cover the height. Oh, shoot. I did this backwards. So the age, we got lucky here. The age actually goes to 39. So I got lucky here. What we did actually works here, but I did it backwards. I was looking at the wrong thing. So you want to actually get age down here. So I should have been looking at the top row of numbers there. So anyway, but we're good because the age and the height are, the numbers are roughly similar. If I had done that backwards, I might have had to go backwards and erase that. Okay, anyway, so the height we need to be able to cover from 2 to 35. So probably a similar sort of thing. How many boxes do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So if you wanted to, we have a lot more boxes here. You could actually, theoretically, maybe go by 2s on this. So I'm actually going to do that. So I'm going to go by 2s on the height. So 2, 4, 6, 8, 10 would be right here. 12, 14, 16, 18, 20 will be right here. 2, 4, 6, 8, 30 is going to go right here. 2, 4, 6, 8, 40 is going to go right here. Okay, so that, I'm going to scale that slightly differently, only because I had a few more boxes there for the height. Okay, the equation for the line of best fit. So what we got to do first is we got to actually plot this. So 1-year-old tree would be 2 feet tall. So we need to go over to 1 for x and then plot a point at 2 for y. So 1, 2 would be right here. Then I need to do 5, 5. So 5, 5. Got to be really careful on these. 5, 5 is actually right there. The 5 is easy to see for the x. It's a little more difficult to see for the y. Okay. Next point, 9 for x, 10 for y. So 9 for x, 10 for y. 9 for x, 10 for y is going to be about right here. 14, 14. So 14, 14 is going to be about right here. 19 for x, 16 for y. 19 for x, 16 for y. Is right there. 24 for x, 22 for y. It's going to be right here. 28 for x, 32 for y is going to be right here. 35 for x, 34 for y. It's kind of nice. They actually gave us one on the corner there. And then 39 for x 35 for y. So 39 for x, 35 is going to go like, kind of right in the middle there. Okay, they want the equation of the line of best fit here. So I'm going to say, let's see. If I had to draw this thing, I'd probably go about right there. Okay. Yeah, that's kind of a tough one. Maybe I would move that down just a touch, but that's good enough for now for you to get the idea. Okay, they want the equation of the line of best fit, so we need to figure out what the y-intercept is and what the slope is. So I'm going to come over here. I'm going to say that y-intercept is probably right at about 1. And then what would the slope be on this? Let's grab another point on the graph. So I don't know, maybe I'm going to grab this right here, like that point right there. So, all right, so we got this. We know the y-intercept is 1, so the b value is 1. What's the slope going to be here? Well, what do we have to do to get from this point over to this point? So I'm going to say, how much do we have to go up? We've got to go up. So to get from 1 to, what is this, 16? So we're going to get from 1 to 16. 1 to 16, so that's going up 15. And then we're going over how much? So we're going to go over from 0 to 15. So that's 15. So that's actually really nice. That slope there is just 1, right? 15 over 15 is 1. So that's kind of convenient. Okay, so what would our equation of the line of best fit be then? The equation is going to be y is equal to 1x plus 1. So what does that mean? That means basically if you want to know the height of the tree in feet, it's going to be basically take the number of years, multiply it by 1, and then add 1. And that's actually pretty close here, right? Like if you look at the age, if you multiply the age by 1 and add 1, that's pretty close to this, right? So like 24 times 1 plus 1 would be 25. That's pretty close. 28 plus 1 would be 29. That's pretty close. 35 plus 1 would be 36. That's pretty close. Okay, notice how they're not all exact. That's okay. We're just trying to get pretty close here. Okay, describe the correlation. I would say this is probably right on the border of being a strong correlation. So I would say there's a moderate slash strong, a moderate to strong positive correlation. Moderate to strong positive correlation. Rough estimate for the correlation coefficient. If I had to guess, I'd say probably about 0.70. Maybe a little higher. Maybe more like 75. But okay. Last question here. How tall would you predict a pine tree would be if you knew it was 50 years old? So we actually have an equation that does this for us, right? Y is equal to 1x plus 1. If you understand how this equation works, it'll do the math for you. What does the x represent and what does the y represent? Well, the x represents the age of the tree and the y represents how tall it is. So you can actually use this equation to plug in numbers, right? If you knew it was 50 years old, what we're saying here is we're saying the height can be predicted by taking 1 times the age of the tree, which is 50, and then adding 1 to it. So, and look, I mean, you could come over and look at the graph and predict that too, right? If you go over to 50 here, you could just come up and figure out what you think it would be. It'd probably be about right here, which is exactly what the numbers give us down here, but it's just looking at the visual representation. So our answer here would be, look, a good guess would be 51 years old, right? So 1 times 50 plus 1. So a reasonable guess here would be 51 years old. Or sorry, 51 feet tall. All right, so there's that one. Example 3, the table shows the number of active woodpecker clusters in a part of the DeSoto National Forest in Mississippi. The scatter plot should represent number of active clusters as a function of number of years since 1990. Okay, so what we're going to do is on the x-axis, the independent variable, that's going to be the number of years since 1990. And then the number of active clusters will be our y value. So Okay, so how many years has it been since 1990 if we're looking at 1992? So basically you can think of this as the x value here is 2, right? It's been 2 years. It's been 3 years here, 4, 5, 6, 7, 8, 9, 10. So when we draw this, we need our x's to be able to cover from 0 up to 10. So how many boxes do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, let's just do each box. Let's just make each box 1. That'll get us up to 10 pretty easily. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then active clusters. Let's see. So we gotta be able to cover everything from 21 up until 61. So how far is that? That's 40 difference there, right? So we got to be able to cover a difference of 40. I always like to include 0 on the y-axis if possible. Sometimes it doesn't make sense to include 0, but it might be kind of nice to include 0 here. How many boxes do we have to work with? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so so we got 20 boxes here. If we take the difference of 40 here and divide it by 20, we can make each box 2, but then I'd have to start at 20, which is kind of annoying. I don't know. Maybe we could do that. You could just start at 0 and go to 100 and make each box 5, right? So 20 times 5 would give you 100. But what that does is it kind of jams the data all to within the middle of the graph. I like the data to be able to be spread out. So let's actually start at 20 down here, and we'll go by 2s. So 2, 4, 6, 8, 30. 2, 4, 6, 8, 40. 2, 4, 6, 8, 50, 2, 4, 6, 8, 60, and then yeah, that'll get us to 61 there. Okay, it might sound weird to you, but there's no like correct way to do this. It just kind of depends on the context, and there are actually a lot of people out there who run statistical studies who are shady on purpose because they're trying to show you like, oh, our viewpoint is correct, and so what they'll do is they'll modify this axis here. It's really obnoxious that people do that, but anyway, all right, let's put some data points down. So 2 should correspond with 21. So 2 comma 21 is going to be that point right there. I'm just looking up at these data points here. 3 should correspond with 28. So 3 comma 28. 4 comma 34 is going to be that dot right there. 5 comma 39 is going to be that dot right there. 6 comma 45 is going to be that dot right there. 7 comma 47 is going to be this dot right here. 8 comma 51 is going to be this dot right here. 958 is going to be up here. And then 1061 will fall right here. Okay. All right, the first thing I want is the equation of line of best fit. So let's see. If I was going to draw a line of best fit here, I'd probably go here. And see, so here's the issue with, I'm going to redraw that a little bit. Sorry. Here's the issue if you don't include the y, if you don't include 0 on the y-axis. So this is kind of annoying. The line of best fit here, I don't know what the y-intercept is. It's going to intersect down here somewhere, right? So that's a little annoying, but we can work around that. You guys are smart. Okay, so let's pick a couple points off here and see if we can get a line of best fit. So I'm going to take this point right here, maybe this point right here. So that's going to cover 2 years sideways, and it's going to cover, what, about 10 feet? Or sorry, 10 active clusters. So right here we're at 38, and then we go up to 48. So basically the slope here is going to be up 10, and then how much are we going over? We're going to go over 2 years, right? So the slope's going to be up 10 clusters every 2 years. So that's basically 5 clusters and then that's per year, right? So 5 clusters per year. So that's our slope. What would our y-intercept be? Well, you know what I'm going to actually do here? I'm going to take this point right here, which is at 3. So we're at 328. Let's think about this. So if you're at 3 years and you're 28, and we know that it's going down 5 every year, let's just do this backwards to figure out the y-intercept. You know at year 2 you're going to be at 23 because you just go down 5, right? You just go down 5 here. So at 1 you'll be at 18, and at 0 you'll be at 13. So basically what we're saying is if we had extended this line, we would know it would cross at 13, which, just looking at it, that looks about right. 13 is probably about right there. So, okay, so our equation for the line of best fit then would be y equals negative 5x plus 13. Okay, describe the correlation. I would say that is a strong positive correlation. Give a rough estimate for the correlation coefficient. I'm going to say this thing's probably like 0.90. I mean, that's pretty good. That line almost hits most of those points. Okay, how many clusters would you predict would be active in 2016? So let's think about this. Where is 2016 on this? Oh, I forgot to label our axes. This is going to be years since 1990. And then this axis over here, I've got to erase some stuff here. So what are we going to make the y-axis? We're going to make the y-axis the number of active clusters. Okay. All right. How many clusters would you predict would be active in 2016? So we got to think, like, where is 2016 on this graph? 2016 is going to be way to the right over here, right? So what would the x value be? Also, why did I make the... I'm sorry. This is dumb. This should not be negative 5 over here. This should be positive 5 right there. I don't know why I said negative 5. Okay. Oh, man. I feel like I might be getting sick, too. All right. Where's 2016 on here? So 2016 would be how many years after 1990? That would be 26 years. So basically what we're going to do is we're going to try to think through, like, okay, if the x number was 26 out here, what would the y value be on this? So, and again, we have an equation that predicts this for us. So what I would do is I would say, look, we know y is equal to 5x plus 13. We are particularly interested in when the when the x value is 26, right? It would be 26 years later. So 5 times 26 plus 13. So that gives you 130 plus 13. So that'd be 143 would be a reasonable guess based off of the math. Okay? And then the last question here, if there were 217 active clusters, what year do you think it is? So this is just going backwards, right? So we know that y is equal to 5x plus 13. We are interested in when the number of active clusters is 217. So what we're going to do here is we're going to plug in 217 for y and then try to figure out x. This is like saying, hey, if the number of active clusters was 217, like way up there, right? What would the x number be that would match with it? So, and we can figure this out with a little bit of algebra, right? So we can subtract 13 from both sides. And then we get 204 must be equal to 5x. And then we can divide by 5 on both sides. And we get that x is, what would that be? 40.8. Okay, so 40.8. Okay, so if the question is asking if there were 217 active clusters, what year do you think it is? Well, so our number, obviously the answer is not, oh, it must be the year 41 AD. Like, that's dumb. What does this number represent? This number represents the number of years after 1990, right? So if we're basically 41 years after 1990, our answer would be, look, it's going to be about I don't know, what's 1990 plus 41? 2031. So it's going to happen in about the year 2031, roughly. Maybe slightly before that, right? Because that's actually 40.8 years. But all right. Hope you guys have a good day. Hopefully I see you guys tomorrow, but we'll see. We'll play it by ear.